Yes, so it's a pleasure to have Professor Claudio Zannoni for the talk, and he will talk about hard and soft packing and molecular organization.
Yeah, very, very simple stuff, really. And of course, it's a pleasure to hear, but also to have a chat. So, well, we're talking about liquid crystals, so as we know, it's something that happens when we melt certain crystals, and instead of going to normal isotropic liquid, you go to this middle state, which is a stable thermodynamic state. It exists in a very well-defined temperature range, and for example, for these molecules here, cyanobiphenyl 5-CB, it will be in this temperature range. So the question is, well, first of all, that these intermediate phases between the crystal and liquid are not just this nematic, which have orientational order and no long-range positional order, but also you have other, so layered one that we will mention, smectics, and the traditional wisdom, at least textbook wisdom, is that these are a stack of 2D liquids. And we'll see if that is true. But anyway, comment on that. And of course, you can have also columnar, discotic, etc. So the question we're trying to comment upon, if not solve, is what are the important molecular interactions that lead a molecule to give a liquid crystal phase instead of just going directly to the liquid. And it is, since we are at the Newton Institute, it's actually a very old question. It's actually mentioned in the preface to Principia that many reasons to suspect that certain forces to the particles of body. And notice that this was before the discovery of molecules, right? By some causes unknown, either mutually impelled towards each other, let's say attracted and coherent regular figures, or repelled, which is basically the same question that you are putting. And actually, a lot, well, a few centuries after that, Lemon, which was one of the discoverers of liquid crystals as we know them now, was still thinking that there was a specific extra force providing orientation, which we know is no such a specific force. It has a nice German name, Gestaltungskraft, etc. So, well, the question is not extremely simple to answer, if it is even possible to answer, because molecules giving liquid crystal, even the simplest nematic and smectic, are not that simple in terms of the number of atoms. We are in the order of maybe 100 atoms for these very simple cases, and they are rigid but also have chains. They're not necessarily aromatic, and they certainly have an elongated structure, which suggests that you could approximate somehow with an object. We'll comment on that. And if you have a discotic one like these triphenylines, they look like, again, kind of disc-like object. But if we try to approach the issue with modeling and computer simulation, we have some problems. One is certainly the one that we just mentioned, that the molecules are complex, they're not so simple, they're not nitrogen or simple argon or simple spherical molecules on which most of the statistical mechanics that we currently use have been based. We have long-range correlation. Indeed, that was the origin of that turbidity in the fluid. Correlation that extends over, well, if it is turbid to the visible light, it means that it has correlation of the order of 500 nanometers, roughly. So huge. It involves millions and millions of molecules. They are anisotropic, so we are observing that tensor. They are soft, in other words, the molecular organization changes with temperature, other parameters, which is actually why they are interesting. And, well, you can have atomistic model with all the detail, or say molecular models where you put an object, and this object, as we shall comment, could be a rigid object, hard repulsive object, that's one line, or it could be attractive and repulsive. Or you can have simple spin models, lattice models. And you can tackle this with theory, in field, two-side cluster, density function, the usual ones. And in the liquid crystal field, it would be Maier-Saupe or Onsager typically, and not a lot more. or computer simulation, Monte Carlo and molecular dynamics, and in the end you try to compare and see. Sometimes it's not easy to have enough experimental results, so we may use computer simulation as a kind of numerical result to test theories, and I'll comment later about that, right? So for example, we could do, well, let's see. First of all, when we compare with experiment or theory versus experiment, we can look at the orientational distribution, the probability of finding a molecule with a certain orientation with respect to the director, the preferred orientation, or more normally, the first few moments, which are called order parameters, we know, so P2 or P4, and then not many other that can be measured for many actual molecules anyway. And in simulation, we calculate this in a scalar way. So if the director fluctuates, we really want to calculate the order with respect to the with respect to the instantaneous director, and if the order fluctuates, it doesn't really matter. So we use scalars, and in practice we use the ordering metric, which turns out to be the same that you use in your theories of the Landau-Lejeune, and we can easily calculate this at every instant of time over the sample, which gives us first average. We can diagonalize it, and the eigenvalues being scalar are good to be average over the trajectory, and that can be used to calculate what we need. And this simulation again could be atomistic or molecular or lattice, and then continue, which of course is not our domain, but somehow it would be nice to connect this case. We can connect the first two, and I don't think you can come down certainly from here, but sometimes it's inevitable because the number of particles that you can treat at this high level are of the order of a few thousand, and these are a few 100,000, and these as many as you want typically in that here. Okay. So let me just introduce the matter by commenting that when we talk of system at equilibrium, what is a minimizer in language will be the free energy, not just the energy, because the temperature would be important. And free energy being, say for example, a temperature, volume, number of particles constant, so-called Gibbs free energy, enthalpy minus Ts, entropy, right? If we have a system, well, okay, we have the usual definition of entropy, a la Gibbs statistical definition, the probability of occurrence of a configuration. I just here to give notation. But, so this probability would be e to the minus u over kt. And if we have a system which is made of purely hard particles, right, the energy of interaction is zero, because the potential is zero if the molecule do not touch, and it will go to infinity if they try to overlap, right? So in this case, temperature is of no effect, because u is either zero or infinite, and when we divide for a finite temperature, it doesn't make a difference, right? So we would expect that the stable system for a hard particle system would be the one with higher entropy, right? The more disordered one in some sense. Is that reasonable? Yeah. This is not true if we have real molecules, say water, for example. This crystal appears more ordered, entropy lower, which is not a problem because the energy is different. We gain hydrogen bond energy, so that compensates the loss of entropy. But if we have a system made purely of spheres, for example, one of these systems, actually the idea of hard particle models is a very old one. These models are in the Science Museum in London, and they go back to 1830. A Professor Daniel, which I could not find the paper corresponding to this. It would be nice to, but there are actually at King's College, I think there are some memorabilia, but not, anyway, these are in, and they're nice, aren't they? So if we have now, just let's not start with liquid crystal, but let's take spheres, right? So if we have a crystal, well, if we have a system of spheres, hard spheres, simple intuition would say that they should not crystallize, because we would expect the entropy of the crystal, nice order system FCC actually, to be lower. There's no gaining energy, right? But if we actually shake a set of spheres, they do happily crystallize, and actually they crystallize at a certain packing sphere. So if you, this is actually a simulation, but experimentally you get a very, very similar result. And that will not go into detail because it's not my topic, but it's a very nice experiment. Just take a plate, Petri dish, and you put little spheres, and then you shake. And you will see that when you have enough spheres, about 50% in volume, they do crystallize nicely. You have no liquid, you have no gas, you have a fluid and a crystal, but you have an order. So why do they order? And the point is that it's not simple to answer, because basically if you think in terms, for example, starting from the ideal gas entropy, which is trivial, is this one, and you take, for example, a van der Waals correction, you say not all the volume is available to the molecule, take away this volume of the molecule, then in a similar way, you should take away the volume that the molecule can pack, but they cannot pack completely. And actually, if you have kind of a random type of packing, you have a jamming, and the maximum that you can get for our sphere is about 64%. But the crystal actually can pack 74%. So if you take this line of reasoning, and that is nice in some papers by Chaik in particular, you see that the system is actually has a lower entropy in the crystal, because actually it packs better, so it can fluctuate more, showing that it's not so easy to predict the result and doing the calculation of entropy. And of course, apart from sphere, you can do all sorts of polyhedra, and this has been done in a kind of systematic and rather 40 postdoc working with one polyhedra by Sharon Glotzer particularly, and she has kind of found, kind of published anyway, this kind of nice table showing that some polyhedra can actually give you ordered phases. So this is a kind of maybe counterintuitive argument showing that you really have to do some calculation to find what is the system with this high entropy, which can be counterintuitive, right? But still we have no energy. And then the point is, how far can we go using only steric repulsion, steric forces, right? And the simplest system we can think, if we are interested in modeling liquid crystal, are spherocylinders. And there's been a lot of work by Dan Frenkel when he was in the Netherlands first, and then probably in Cambridge also. So if we take spherocylinders, so basically you have a rod, capped with two spheres, so there will be L plus D, if D is the diameter of the radius of the rod, sorry, that will be the length, and you have width, which is D, the diameter of the sphere, and then you have an aspect ratio. So, and Frenkel, Dan, and collaborators have developed this phase diagram for spherocylinders, showing that you have various phases. You have pneumatic, isotropic, of course, smectic, pneumatic, and solid. And what you get, what you can get, depends on the aspect ratio. And we'll come back to this point later. So, right? So this is not Onsager theory, even though it's still based on a hard particle. This is kind of numerically exact solution, right? The point is, do we comply with this when we have real molecules? So we come back to that. Also, if we look at the dynamic aspect, if we look at the dynamic of this, right, the conventional wisdom that I mentioned before would say that if a smectic is actually made of a stack of fluids, it would be easier to move in the layer plane rather than across. So the parallel, which is higher than the perpendicular in the nematic phase, because it's easier to slide the molecules along the director, should have the opposite behavior in the smectic. And this actually turns out to be the case, at least for a fluid where the spherocylinders are fully, perfectly aligned. These are all calculations by Kofke and Evans. Yeah. So you see, in the nematic, it's the ratio D parallel is about 9. In the isotropic, in the smectic, is the reverse, as you would expect. So this is kind of textbook-like happening. If we take hard ellipsoids, which are another reasonable shape to use only with hard particles, this has been also studied in detail by Frenkel, Michaelen, many others, and recently taken up again by this group, Audriozol, etc. And that's the phase diagram that they get. It's a nice phase diagram. You can have elongated ellipsoid or squashed ellipsoid, and you get nematic, isotropic, you get crystal, but you do not get smatic. So hard ellipsoid cannot give smatic. And the argument is, this is probably more for a rigorous mathematical thing, which I'm not sure is available as a proof, but the intuitive thing is that if you have a fully ordered packing of ellipsoid, you can do an affine transformation on the size of the ellipsoid and map this into a sphere system. And then when you have a sphere, what's the difference between a crystal and a smatic? But I'm not aware that there is a rigorous information. Certainly you do not get that thing. So I cannot tell you if it complies parallel, perpendicular, and smatic, because there isn't one. Yeah. Now, if we switch on attractive interaction, the kind of paradigmatic anyway, simplest interaction that we use, and other groups have used a lot, is so-called gay-Baer, which is kind of similar to the Lennard-Jones that we mentioned before. But of course, since we have elongated, or anyway, anisotropic particles, the potential is a lot more complicated because it will depend not only on R scalar, but it will depend on R vector. In other words, this and this interaction are different. And it will depend on the orientation of molecule 1 and 2. But you still have the kind of contact distance, which depends on this parameter, and you have a potential well depth, which is different as you approach the two molecules in different directions. And if you do simulation at different temperatures, you get isotropic, nematic, smatic. Isotropic, nematic, smatic, just changes the temperature. So it's, because here the temperature, of course, is important, because the energy is finite. This is for an aspect ratio of 3, which would have difficulty in the purely hard system, even ordered system. And you can have squashed ellipsoid and you form columnar spontaneously. Now, if we look at the smatic, it is maybe interesting that the diffusion coefficient, which you obtain in simulation by Einstein dilation, looking at the mean square displacement and waiting for the mean square displacement over time to be linear. If it ever gets linear, then it will be diffusion, and then you will get the diffusion coefficient. So if we look at the mean square displacement in the nematic, the slope, which is the diffusion coefficient, is bigger than the x and y, which are equal because it's uniaxial, which is okay, it's normal. Experimentally, you do get as well, as for 5CB, for example, the parallel is bigger than the perpendicular. Yeah. But if we go to the smatic, actually the motion is easier along the director than perpendicular to the director, which is either wrong or it means that the simplified textbook idea that the smatic is a stack of two-dimensional fluid is not completely correct, because here it's still simpler to jump from one layer to the other than actually go in the plane. And actually, experimentally, this is what happens in a number of smatic, not in every smatic, but in a number. So in this one, for example, you see isotropic. This is 6 OCB, but it's not interested in the chemistry at this moment. So the parallel is bigger than the perpendicular kinematic, as you expect, but it keeps to be the same also in the smatic. Yeah. So I think this again would beg some questions, maybe from the mathematical point of view. To what extent you can switch from one to the other type of dynamics, which is not obvious. And then if we turn to a more general question, I mean, we have only showed the simplified molecular models now, either steric or repulsive plus attractive. But to what extent can these models reasonably approximate real molecules? Yeah? Obviously, there are some cases where you have chains, flexible chains, etc., which they are not particularly appropriate, you would expect. But in this case, for example, quinquephenate, P5, you can call it phenyl. I mean, this is a pretty rigid molecule, no chain. It's very easy to form liquid crystal, unfortunately, this is a complication because it's so easy to form a liquid crystal. The liquid crystal is maintained up to something like 500 degrees, where the molecule like to decompose. So, yeah, because you can carry it to high temperature and still be a liquid crystal. But the point is, I mean, this was, by Ed Samulski, that we know as a scientist that has been in the liquid crystal field for even longer than most of us. And they said that, well, if there was even a calamitic is another word for this elongated thing, mesogens that correspond to essentially to a rigid rod, then it would be this one, or one like this. So we did a fully atomistic simulation on this, and then we said, well, can we use this to test if it is a rigid rod? Can we test if it is Maier-Saupe or Onsager type theory? I mean, just, and so we took, well, you can take the full chemical structure, you work out some quantum chemistry to the geometry to get the internal torsional potential, and you have some parameters to optimize to try to capture the effect of the molecules beyond the two that interact directly, of the environment, if you like, and define a force field, and then just you solve Newton's equation of motion for this kind of, well, kind of order of magnitude of, say, 50 to 100,000 atoms. And then when you're satisfied that it is equilibrated, you compare with the experiment. So I will not bother you with the force field, which is partly due to intramolecular terms, which are corresponding to the spectroscopic, vibrational, infrared spectra. The non-bonded are kind of Lennard-Jones, again, trying to capture the repulsive nature and the attractive dispersive nature, and then electrostatic, which is very important. I'll come back to that. You could say electrostatic, these are neutral molecules, yes they are, but the partial charges on every atom are not the same. They are very different because every atom has a different electronegativity. So that's the molecule. And then it is nice theoretically because it has only two types of atoms, carbon and hydrogen. So you can test also to what extent it is important, the tuning of the potential that you do. So, okay, doing quantum mechanics, so this is not too complicated. You can do it at different levels of theory. Basically, you always get the phenyl ring, both the outer and the inner one have an angle of about 40 degrees. So they're not flat, they are kind of twisted. But okay, this can be dealt with, it's not a problem. Then in the non-bonded part, you have to tune the Lennard-Jones potential well depth. And this is maybe interesting because you could be tempted to say, take the value that you get from quantum chemistry or that you get from one of the common force field that you can download from the net. And they are badly wrong in terms of giving. So you don't, if you use the best quantum chemistry available from Georgia Tech, Cheryl, etc., this is even out of this scale. So here we plot simply the density of the system that you get when you tune the potential energy of the carbon to be the value on the x-axis, right? And that's the experimental density. So if you don't tune this is the only parameter that is fitting in the whole of the calculation, only thing. If you don't, if you take the common amber or char, you don't even get the density correct. You don't even get the phases correct. And if you take the quantum chemical one as well, because it's just the quantum chemical is very nice, but it is for two particles at 0 degree Kelvin in vacuum, which is not exactly the environment of the molecule, right? So, but if you tune this, then this is what you get, the order parameter P2 and P4 versus temperature, and it has a transition. Obviously, it doesn't go exactly to 0 because this n molecule would go to 1 over square root of n. If it was 0, it would be fat. I mean, statistically, it has to go to, it goes to 0, approaching it from above with the square root of the number of molecules, 1 over square root of the number of molecules. So anyway, this is clearly a transition, and there is some other transition. So we find nematic, smatic, crystal. Actually, we find more than one smatic. And now, when you compare to experiment, I mean, being naive theoretician, you would say that you compare with experiment, and that's it. Transition temperature, that's it. But there are at least 1, 2, 3, 4, 5, 6, 7 groups and some with a Nobel Prize in them, that have measured the transition. And if you look at the nematic isotropic, it goes from 698, 691, 700, 699, which is huge for a transition temperature. I mean, you go to your doctor and give your body temperature 2.1 of a degree. I mean, if you give an uncertainty of 5 degrees or 7 degrees, he'll be kicking you out of his office. And so we get it 715, which is a little higher, but it's of the order of say, 2%, 0%. So, but now we can plot our result for the order versus the experimental order parameters that are available, that coming from different measurements, and mean field theory. Yeah? So this is mean field theory are the red curves, and you see mean field is Maier-Saupe, but okay. You see that the slope is rather different from the experimental one. The experimental one that we get, these are the blue full symbols, are, I think, in good agreement with various measurements. And the one that deviate a lot more are wide angle X-ray, but there may be some problem in interpretation. But the most straightforward measurement, the deuterium NMR, is an excellent agreement with our one. And we can also predict before that has not been measured, as far as I know yet. Now, given this order parameter, and given that this should be a route, can we say something about Maier-Saupe, Onsager, or something? Well, let's remind. 10 minutes more, is it?
Oh, yes, 10 minutes, yes. 12.
Okay, so I'll be very quick. But just to remind you, Maier-Saupe basically starts from an intermolecular potential and does some very drastic averaging. It averages over all the orientation of the intermolecular vector, assuming that it is spherically distributed. Averages formally over the distances, and averages consistently being a mean field theory on the orientation of a second molecule. So you get a potential of this type if you start from a second rank potential, or a fourth, similar one if you start from a fourth rank or whatever. But this is the simplest, what is called Maier-Saupe. So originally it was said that it was due to an isotropic polarizability van der Waals, but it doesn't have to be, but just as long as the functional form is similar. So basically, this would be physically a Maier-Saupe model. It would be a little anisotropic center inside the sphere, because there is no dependence on the intermolecular vector, which seems crazy. But you get P2 and P4. And Onsager, actually, it's not in bad agreement with many experiments, maybe you have more chance, but I'll comment on that. While Onsager, as you know very well, some of you have worked in detail and on rigorous basis, is a second virial approximation to the chemical potential. It predicts a first order phase transition, but the order parameter transition is far too large, something of the order 0.8, 0.5. You can do better theory, but it's still very bad. The entropy jump is huge. I mean, the entropy jump is kind of an order of magnitude larger than real, and it works even for long graphs, but not for small units. What about what? But from the point of view of P2 and P4, this was the original ansatz of Onsager, but then you can rewrite this in terms of a sum of the Jean polynomials, as various people have done, Lasher, Ishihara, and actually this converges fairly well. So basically the first approximation is similar. So if we plot P4 versus P2, then this is actually showing that P2 and P4 obtained from the simulation of quick P are in excellent agreement with the P2 type distribution, not necessarily Maier-Saupe, could be either. And also actually I worked out a long time ago a simple algebraic, I mean this is not a fitting, it's done with computer algebra, just using this to get an expression for P2, one for P4, and doing computer algebra to eliminate A2. And this very simple approximation that you can use for fun actually works very, very well in the order. And this is another approximation instead from continuum theory from Tom Faber. We were here in Cambridge a long, long time ago. But anyway, point is, as long as the distribution is like this, to a good approximation, you cannot use them to distinguish. But you can look at the aspect ratio, and now this is not Onsager. We go back to Dan Frankel and collaborator diagram. And now we have to input an aspect ratio. So if we actually measure the aspect ratio post hoc for our molecule, not just from the formula, then then we have values that are compatible with, as we showed, isotropic, nematic, smectic. But if it was strictly a rigid rod, we should not have. We should not have. Well, the aspect ratio is here, as you can see. So we should not have a nematic or a smectic. But molecules don't know, and they do, and they don't know that they have to be rigid. Indeed, if we measure the bending angle of quinquephenyl, we find that it's not so rigid, completely rigid. It's not a delta function. It is a kind of, can be 20, 30 degrees and shorten the aspect ratio. But yet, it is, I mean, you have attractive forces. So now, why do the Onsager or theory in particular, I think, don't work very well? Point is that in a fully hard particle theory, isotropic is really isotropic. You do not have correlation, and that explains the big jump in entropy and other parameters. But if we look at the radial distribution of quinquephenyl, for example, across the transition, this is two curves here, you see that they are essentially the same, which is supporting a very old model that we did when I was a student, actually long time ago, which is very easy to explain. In those days, it was just an hypothesis, and the idea is very simple. If we have a rod here, and we pack with another one, the aggregated we form is less anisotropic than the single molecule. We pack another and another, then it becomes more spherical. At a certain point, there's not a lot of advantage to add another molecule in the same direction because the aggregate has become nearly spherical. So in a way, a liquid crystal has essentially the same local structure of a liquid. It's just that this nearly spherical cluster, which are in a perverse way similar to the one that Maier-Saupe theory were assuming, this local cluster become overall ordered, and then you have P2, P4, whatever you have, an isotropic system and nematic. But at a local level, the order is not destroyed completely. And the Onsager type theory do not capture this because they assume disorder here, like you have. So I think that's the reason. What about the diffusion coefficient? Well, diffusion coefficient is a bit complicated actually. So if we start from the nematic, okay, it's easier moving along the director, and in this first smectic, then what we find anyway, this has not been found experimentally, not studied experimentally yet, is that there should be another smectic with more kind of crystalline type order, maybe it's smectic D or whatever, where actually it is easier to move in the plane, as you would expect, and then certainly in the crystal. But it is kind of complicated. So I have certainly a few other examples, just to say, maybe I just show you the titles and skip, so I leave. So what should we do to add realism? Well, we should certainly have, this is for theoreticians, find a way of adding flexibility somehow, because in most real molecules we have chains, and chains are very important, because if the chain is short, you have no liquid crystal. If it is 5, you have a nematic, and if you go up to 8, you have smectic. So it's not just a matter of aspect ratio, because you have an odd even, but I mean, simulation-wise, we can get the transition temperature to within 2-3 degrees. But let me comment again on the importance of attraction and repulsion. So we did HCB in detail, so we can obtain the spacing correct, which is not completely trivial, because to get the spacing correct, the molecule pack in this anti-parallel way, and in a way that is not even obvious, isn't it? I mean, it's obvious that if you have a cyano, which is a strong dipole, sort of 5 dBi, yeah, another cyano should place anti-parallel. But you would expect them to pair like this. But if they did, the spacing would be much bigger than what it is in reality. So the pairing is actually, I mean, these molecules are interdigitated a lot more than the simple intuition would suggest. But this is what experimentally, at least 3 groups find in X-ray, and our simulation without any fitting are within 1 angstrom. But a group of Hannah and McDonald, not McDonald, that was here in Cambridge, that did study HCB, a simulation you can switch off part of the interaction. So they switched off the electrostatic interaction. So now, question was, how important is to model the shape in detail? Here the shape is modeled in detail, because they have all the atoms, everything, but the traction is not, because they've switched off the charges. And they do not get the transition, you see? They do not get the transition. It's wrong by tens of degrees. You don't even see it very well, and it doesn't form an antiparallel type of diamond. So, I mean, one cannot avoid to have interaction. And okay, I had something on elastomers where we had to switch to go to more soft potentials, and that okay. So this is, we define the soft gay pair. Point is that if we use a normal gay pair connected by springs, you cannot simulate the polymer or the elastomer. But if we soften the repulsive part of the potential, then there is a little partial interpenetration that allows for the change to go past one another in a way that for real molecules would be allowed by the flexibility. So with this, with Gregor Skace from Ljubljana, we have simulated a number of elastomers and reproduced experiments, for example, by Urayama in Japan, and also the soft elasticity. So let me just go to the conclusion, because I just had other example trying to show that both are important. But I would like to quote, I mean, Chandler-Wicks and Anderson are normally well known for saying that only repulsive are important in a way, isn't it? But if you look in one of their papers, they actually say that the realistic shape and flexibility of the long molecule will undoubtedly have to be taken into account in comparison with their experiment. And I think that now, with the progress in simulation and the progress in experiment, we've gone to the point where we do have to take into account both. And there isn't a single important relevant intermolecular potential. Packing is very important, especially at local, and it will be conserved through the nematic isotropic transition, but attraction can be neglected. And molecular flexibility, if you are developing a new theory, I think should be included. And I don't know of any kind of Landau design theory which allows for some flexibility, deformation, something like that. And that maybe is a possibility or not, I don't know. And then with atomistic simulation, we have enough data actually to compare with theory and test this. And this is probably the most important slide, because of the people that have done the work. For the atomistic, Otello, Luca, Matteo, Mattia, and Antonio, and for the Gay Byrne and Coarse-Grain, Silvia, Lara, and Roberto, and the agency, and of course you for your kind attention to this. Thank you.
Questions? We have time for questions.
Yes. So, Claudio, great talk, and I think it's a really much more complex subject than it seems to be at first glance. So my question might be overly simplistic. I'm just sort of getting myself out of trouble there already. So as an experimentalist, if I do X-ray scattering from a smectic system, right, I definitely see the first Bragg peak, and I might see the second Bragg peak. And of course, there are a number of ways that we could interpret that. But the simplest way is to actually say that what we have in the smectic system is a sinusoidal or very close to sinusoidal density wave. And of course, none of the simulations, they show much more, the density wave is much more like a square wave, where you, no?
The atomistic simulation is not.
So, to me it looked, you would see maybe an interpenetration of these smectic layers, which is,
also in simulation.
so you're getting that, but for the spherocylinders, not really. No.
These are different things. No,
Yeah,
I'm talking of
So for the
atomistic simulation, you get to the detail.
yeah.
But to me, I think that most X-ray experiments have been interpreted in a perhaps oversimplistic way.
Yeah, absolutely.
And this is particularly for the smectic And if you notice in literature, it's very difficult to find what should be the most trivial thing, the translation, the positional order parameter.
Yes.
Right?
Yeah.
So, cos 2 theta, cos 2 pi zeta over d.
Yeah.
Yeah, there are a few, and actually these are the only things that don't agree very well with our simulations. And I think the reason is that when you interpret the X-ray, you tend to interpret the first Bragg peak, well, in terms of just positional order parameter. But actually, you have also a contribution for the mix, orientational, translational order parameter, which is non-negligible. Yeah. And if you allow for that, then you should be able to get from experiment both the positional, the orientational, of course, from the angular dependence, and the mixed one. And that has not been obtained. So if you have a case where you get not only the first, and of course, as you know much better than me, it's very difficult to have absolute measurement. So if you have a system where you get at least two, and possibly maybe if you see the third spot, then you should be able to do that. But it's difficult, and for neutron as well, it would be difficult. But atomistic simulation would give you, we could actually give you kind of predicted numbers, and maybe yes.
Are there any, can you yourself work on chromonics, chromonic molecules?
A little bit.
So is there a picture for, say, transitions from isotropic to columnar and maybe to toroidal phases? Are we far from that?
Yes, I think yes is the simple answer. No, there are some nice, nice simulations by Mark Wilson in Durham. Has done some, but it's very complicated. I mean, so Viscotic is simpler because chromonic is complicated. The simplest model that many have tried, also we did not publish because it was not, is to use to have a chromonic. So a chromonic, for the one or not, it is a kind of amphiphilic molecule with a positive and negative part, but based on a rigid aromatic core, and the charges can would be on the periphery. So it's very different from a soap. Actually, Oleg is Lavento is anyway. So the simple model you could think theoretically would be to have this charge disk in a continuum, and then assume a certain dielectric constant for the continuum and do simulation. But that does not work very well. And part of the reason is that the dielectric continuum, well, the water has a dielectric constant of 75, sort of, which changes with temperature quite a lot, but it's defined at microscopic level. When your molecules are getting close together, then the dielectric constant will have, if you have a Fourier expansion, will Q dependence on R dependence, and that does not work very well. So you would have to put, atomistic water in, etc., which is doable if you have to do it once. If you have to do a lot of cases, a lot of concentration, a lot of temperature, it becomes complicated. So Mark has shown that you get columns that form and dismantle and assemble, but your question would be essentially, can you get the phase diagram out? I'm not aware of that. But even experimentally, there are not many phase diagrams and not very detailed. So there are a couple for this system that Oleg also studied, Sunset Yellow and Chromoline, but there are not a lot of experimental data available for chromonics. And so you've chosen a complicated case, a very complicated case. And also, I mean, yeah, but good system to study. It's not a trivial one. None is trivial, but no.
Thank you. So anybody else? Well, if not, we go for cheese and wine. Thank you very much.